Assalamu alaikum. This is the lecture 12 of data security and encryption, and the topic of this lecture is Advanced Encryption Standard, abbreviated as AES. So here are the lecture contents. In this lecture I will give you a brief overview of finite field arithmetic, which was discussed in the last two lectures, and then we will move to the advanced encryption standard structure. I will provide a general structure and with a detailed structure along with some examples. Then we will look at AES transformation functions. There are four transformation functions in advanced encryption standard, named as Substitute Byte Transformation, ShiftRows Transformation, MixColumns Transformation, and AddRoundKey Transformation. So at the end of this lecture, you should be able to present an overview of the general structure of Advanced Encryption Standard and understand the four transformations used in the Advanced Encryption Standard. So the Advanced Encryption Standard was published by National Institute of Standards and Technology (NIST) in 2001. Advanced Encryption Standard is a symmetric block cipher that we have already discussed in previous lectures, and that is intended to replace the data encryption standard, which was also discussed in previous lectures, and it was approved standard for the wide range of applications. So before moving forward, let's overview a summary of finite field arithmetic. So in advanced encryption standard, all operations performed on 8-bit bytes. That means every operation will be performed on a byte or set of bytes. The arithmetic operations of addition, multiplication, and division are performed over the finite field of GFF 2 raised to power 8, which was discussed in the last lecture. So a field, important consideration about a field is a set in which we can do addition, subtraction, multiplication, and division without leaving the set. That means the result of any two operands, addition, subtraction, multiplication, and division, will be a part of that set. Then this set will be called a field. So it is necessary for a set to be filled to perform such operations. The division is defined as A over B is equal to A into B inverse. So an example of finite field with a finite number of elements is a set Z of a prime number P consisting of all integers ranging from 0, 1 to P minus 1, such as if we say the example of finite field Z8 consists of integers from 0, 1, 2, 3, 4, 5, 6, 7, which is P minus 1. So where P is a prime number and in which arithmetic is carried out on modulo P. So another consideration is that P must be a prime number, that you cannot create a finite field of any non-prime number. And all the arithmetics such as addition, subtraction, multiplication, and division is performed using the modulus P. So you must have seen these examples using the modulo 7 and 8 in the last few lectures, and we have considered that the modulo 7 set is a field, while the modulo 8 set was not a field because it does not involve the prime numbers, and there was no uh, inverse multiplicative inverse for all the numbers in modulo 8, and there was multiplicative inverse for all the numbers in the modulo 7. So virtually all encryption algorithms, both the conventional and the public key encryption algorithms, involve arithmetic operations on integers. So if one of the operations used in the division arithmetic algorithm is a division, then we need to work in the arithmetic defined over a field. So it is a precondition that division requires each non-zero element have a multiplicative inverse, as it has been discussed many times that your field must have the multiplicative inverse of each element except the element 0. So for convenience and for implementation efficiency, we would like to work with the integers that fit exactly into a given number of bits with no wasted pattern, that we have seen in the last example, that we have used a 2 raised to power 3 field in which all the bits were covered and no bit was wasted. However, the AES used 2 raised to power 8 bit pattern. So integer in the range through 2 raised to power n minus 1. For example, in this case we had 2 raised to power 3 and we had the integer 0 to 2 raised to power n minus 1, 0 to 7. So if we have 2 raised to power 8, we will have the elements to 0 to 255. So set of integers as defined as the integer set z, which was referred for a modulo number, is using the modular arithmetic is not a field. For example, the integer 2 has no multiplicative inverse in z2, that is, there is no integer b such that 2b mod 2 raised to power n is equal to 1. Similarly, there is a way of defining finite field containing 2 raised to power n elements. Such a field is referred as gf 2 raised to power n. So a finite field containing 2 raised to power n elements is referred as gf Galileo's field 2 raised to power n. So every polynomial in this kind of field can be represented by an n-bit integer, which was discussed in the last lecture when we replaced the polynomials with the number of bits, such as in 2 raised to power 3 we use 3 bits 0 0 0 to 1 1 1. So you can consider a set of all polynomials of degree n minus 1 or less with the binary coefficient. So thus each polynomial has the form as described in many earlier lectures, that the polynomial contains the form of summation I from 0 to n minus 1, and we have a coefficient a of I, and then we have a variable x, which has the power a of x of I. So for where a of I can take the value 0 or 1, that means you can have 1x or 0x, that means you can omit any power of x. So in case of 2 raised to power n different polynomials in the set S, we have n is equal to 3 and 2 raised to power 3 is equal to 8 polynomials, as discussed in the last example. So those polynomials were 0, 1, x, x plus 1, x square plus 1, x square plus x square plus x plus 1. So this figure shows the overall structure of an advanced encryption standard algorithm encryption process. The cipher takes a plaintext block size of 128 bits, or in other words 16 bytes. The initial state vector is a 16 byte vector, and it is formulated in 4 by 4 grid. The key length can be 16, 24 or 32 bytes, as described here. The algorithm can be referred as, if it is a 16 byte length, then there will be 128 bits in 16 bytes, then it will be referred as AES 128, For the second, it will be referred as AES 192 as it will contain 192 bits, and for the third, it will be referred as AES 256 depending on the size of the key length. So plain text is a 16 byte or 128 bit, and we have a key of similar. For example, in the first case we have 16 byte key, and then we can use the 10 rounds of transformation. So in the initial transformation, there is only one transformation is performed, and then there is a 10 rounds of transformation, and in each round there are 4 transformations. However, in the final round there is 3 transformations. Then we will get a final state of 16 bytes in 4 by 4 grid, which will be converted into a 16 byte or 128 bit sequence of cipher text. So the input to the encryption and decryption algorithm is a single 128 bit block as discussed in the last slide. This block is depicted as 4 by 4 square matrix of bytes. So each block contains 1 byte. So this block is copied into a state array which is modified at each stage of encryption or decryption. So after the final stage, the state is copied to an output matrix. So there are a number of transitions on input vector or input grid, and there is number of state arrays, and then finally we get the output of our matrix. Similarly, key is depicted as square metric. Again, the 16 byte key is used, and there will be total 128 bits. So this key is then expanded into an array of key schedule words. So it shows that the expansion of 128 bit key, uh, each word is a 4 each word is a 4 bytes, and the total key schedule is 44 words for 128 bit key. So this can be done by one initial transformation, and then 10 rounds of transformation multiplied by 4 transformation in each, and in final round we get 3 transformation. In total we get 1, 40 and 3, that is equal to 44 keywords, and this is for 16 byte key. Note that the ordering of bytes within the matrix is by column. So for example, the first 4 bytes of 128-bit plaintext input to the encryption cipher occupy only the first column in the input matrix. Then the second 4 bytes occupy the second column, and similarly third and fourth column. Similarly, the first 4 bytes of expanded key, uh, the first 4 bytes of expanded key, which form a word, occupy the first column of the matrix W, and so on. So for each AES encryption, the cipher consists of n rounds, where the number of rounds depend on the key length. And the rounds we depicted that in the last example there were 10 rounds for 16 byte key, and we had 12 rounds for 24 byte key and 14 rounds for 32 byte key as depicted in the example. For example, in the first case we can have 128 bits of key, that will be equal to 16 byte or 4 words in the AES 128 bit. Similarly, we can have 192 bits of key size or 256 bits of key size. Similarly, the plain text will be similar in all the different implementation of AES, and the word size will be 128 bits. There can be varying number of rounds. For example, in the 16 byte AES we have 10 rounds, and in 192 bits we have 12 rounds, and in 256 bits we have 14 rounds of AES encryption. Then for each round we have different key sizes which are similar to the key size of our AES encryption algorithm, except that the word size is similar for all the encryption algorithms. So we can expand the keys, as we have seen in the first example that the key was expanded to 44 words in the 16 byte key, and similarly if you have 24 24 byte key, you can expand it to 52 words, and similarly if you add 2 more rounds you can add 8 more words and make it to the 60 words of key expanded key size. So the first n-1 rounds consist of 4 distinct transformation functions. These functions are named as subbytes, ShiftRows, and MixColumns, and AddRoundKey, which will be described in the next few slides. The final round contains only 3 transformations, and there is an initial single transformation AddRoundKey before the first round, so which can be considered as round 0. So each transformation takes one or more 4x4 matrices as input and produces a 4x4 matrix as output. So the figure shown above shows that the output of each round is 4x4 matrix, with the output of final round being the cipher text. So also the key expansion function depicted in the above slides generates n plus 1 rounds of keys, as we have 10 rounds in the 16 byte AES encryption. There were 10 rounds of keys plus 1 round of keys, each of which consists of 4x4 distinct matrices. So each round key serves as one of the inputs to the add round key transformation in each round. So this figure shows an AES encryption and decryption mechanism in more detail. So it indicates the sequence of transformation in each round and showing the corresponding decryption function. So as it is evident that encryption proceeding down the page and the decryption proceeding up the page. So this shows the encryption and this shows the decryption process of our AES algorithm. So as you can see again, we have initial plain text that is met with the one transformation known as add round key. Then we have number of transformations in each round, mainly named as first transformation is substitute bytes, in which you substitute the byte of input matrix, and in the next transformation you shift the rows from by applying the left shift or right shift operation. In the next transformation, you apply the mix column transformation, in which you multiply columns with the with any of other randomly generated matrix, and in the final transformation, you add the round key from the matrix generated from the add round key. So these steps are repeated for 10 times in 16 byte AES transformation, and the cipher text will be generated after the 10 rounds. And at each round you are embedded with the add round key function from the round key set. In the decryption process, you perform the inverse shift rows, inverse subbytes, and add round key, and inverse mix columns. And then you perform the number of steps in the decryption process, and finally you get the initial plain text. So before diving into the details, we can make several comments about the overall AES structure. So one noteworthy feature of this structure is that it is not a Feistel structure discussed in lecture number 5 or 6 or 7. Recall that the classical Feistel structure in which we have half of the data block is used to modify the other half of the data block, and then halves are swapped. However, in AES, the entire instead of processes the entire data block as a single matrix during the each round is used for substitution and permutation. So the key is provided as input in is also expanded into an array of 44-bit words. So there are 4 stages to perform the AES encryption rounds, and the first stage is a substitute byte, and it uses a substitution box to perform a byte by byte substitution of the block. That means you have a predefined block for example, in the 16-bit you have 16 byte block, and you perform the substitution on number of bytes from the substitution box set. Then you perform the shift rows using a simple permutation of the rows, and you perform the left shift or the right shift operation to change the change the rows to achieve the permutation. Then you perform the MixColumns transformation. It is a substitution that makes use of arithmetic operation over g of r to the power 8. And finally you perform the AddRoundKey transformation. It is a simple bitwise XOR of the current block with a portion of expanded key as the key set generated by the algorithm in the start with the number of words depicted in the above slides. So there are some other important consideration regarding the structure of AES, that the cipher begins and ends with the add round key stage. So you have seen this example that the structure is very much simple, and for both encryption and decryption you have this step which have the add round key stage. So it is followed by the 9 rounds, and that each includes all 4 stages, followed by the 10th round with 3 stages. So you can view the cipher as alternating operation of XOR encryption, add round key of the block, followed by the scrambling of block of the other 3 stages, followed by the XOR encryption, and so on. So in AES, each stage is easily reversible, and the decryption algorithm make use of expanded key in the reverse order. However, the decryption algorithm is not identical to encryption algorithm. So in the Feistel structure we have the same encryption and decryption algorithm. However, in AES, encryption and decryption algorithms differ from each other. So once it is established that all 4 stages are reversible, it is very easy to verify that decryption does recover the plain text. So at each horizontal point, state is the same for both encryption and decryption. And finally, the final round of both encryption and decryption algorithm consists of only 3 stages. So this diagram shows an AES encryption round in more details. It is depicted that initially we have a state matrix of our input matrix, which is complemented with a substitute bytes from an S box, and each state matrix is substituted using a substitute box, and we get a new state. So this is the first transformation, and in the second transformation we perform the shift rows. That means in each byte is shifted either from right to left or left to right, depending on the mechanism of our AES encryption. And then we get the second form of our input state. It is met with the mixed column transformation, that you perform a mixed column transformation using a multiplication matrix of a randomly generated matrix, and then you get the third transformation state, and finally you add the round key from the round key uh, expanded transformation to actually get the final state of each round. And after each round the steps are repeated in the similar order. So now we can turn to a discussion of each of the four transformations used in the AES description. So for each stage we describe the forward encryption algorithm and the reverse decryption algorithm and the rationale at each stage. So as discussed, the first step is the substitute byte transformation, and it is done in the forward and reverse transformation. The forward substitute byte transformation, called sub bytes, is a simple table lookup. That means you have an input state of your plain text, then you have a lookup table of S block or S box, and that uh, this table contains a matrix that you swap the values of any of the bytes from here to the table here using the location of your matrix x y, and then getting the location from the S box, and then you will get the resultant substitute byte transformation. Similarly, AddRoundKey transformation is done from picking up a column from our state matrix, and then a word from the expanded key matrix, and then we perform the exclusive OR operation and get the resultant transformation. This diagram shows an AES definition of 16 by 16 matrix of byte value called an S box or substitution box. So it contains a permutation of all possible 256 8-bit values. So each individual byte of state is mapped into new byte using this way. The algorithm said that the leftmost 4 bits of the bytes are used as a row value, in the rightmost 4 bits of are used as a column value. These row and column values serve as indexes into S box to select the unique 8-bit output. For example, the hexadecimal value of 95 we consider for the example in the initial state box is taken, and for reference it is referred as uh, for row number 9 and column number 5 on the substitution box. So if we look at the row number 9 and column number 5, we get the substitution byte value of 2a. So according to this table, the value of 95 is mapped onto the value of 2a. So this diagram shows the construction of a substitution block. or substitution box. So as depicted earlier, that you get a value in the xy form, a byte at the row y, and the column x is initialized as yx. So you can initialize a substitution box with the byte values in ascending sequence, row by row. That means your initial row will start from 0, 0, 0, 1, 0, 2 to 0 f, and for each row you increment 1, 0, 1, 1 up to 1 f, and so on up to ff. Thus, the values of the byte at row y and column x is referred as yx. Then in the second step, you map each byte in the x box to its multiplicative inverse in the finite field of g of f to the power 8, and the value of 0, 0 is mapped to itself. So you can consider each byte in the X box consists of 8 bits labeled as bits from bit 0 to bit 7, and then you're going to apply a transformation to each bit of the byte in the X box. So the AES standard depicts the transformation in the matrix as follows. So this is the transformation matrix for AES to transform into an S box. So each element is in the product matrix is the bitwise. Each element in the product matrix is a bitwise XOR of the products of elements in one row and one column of bits. Then as a result, the bit column is transformed into a vector of bytes, and it will give you a S box value of yx. Similarly, when performing the inverse function, you can calculate the inverse of y of x, and in this way you perform the inverse function first, and then you convert the bit column to a vector byte, and then you will get the initial value of x. Or in other ways, if you get the value of y of x, you perform the byte to bit column vector. Reverse of this step is here, and then you perform the multiplication of the vector, and then you do the bit column to vector byte and inverse of your uh, g of f to raised to power 8, and then you finally get the inverse of your inverse s box of your value. So this shows the inverse substitution box, and it is called inverse sub bytes, and it makes use of the inverse s box. And the note, for example, we have discussed earlier that we get 95 s box value of 2a, and the procedure to output 95, and the s box produced 2a. The inverse s box is constructed by applying the inverse in the transformation. So in this case we get the value 2a, and we get the initial value 95. So here is a rationale for using substitution box. The substitution box is designed to be resistant to known cryptanalytic attacks. So the Rationale developers sought a design that has low correlation between input bits and output bits. That means the input and output bits differ in large amount of bits, and the property that output is not a linear mathematical function of the input x. This non-linearity is due to the use of multiplicative inverse function. So after the S box transformation, The next transformation is referred as ShiftRows Transformation, and it is done in the forward direction in the encryption and inverse direction in the decryption. So the forward shift row transformation is called ShiftRows, and it is depicted in this above figure. The first row of the state is not altered. As you can see, it is the same row as the output state. The second row, on the second row, you perform the 1 byte circular left shift. That means you shift the second value to the first, and the third to the second, and fourth to the third, and the first value is transformed to the last column. And for the third row, a 2 byte circular left shift is performed, and for the fourth row, a 3 byte circular left shift is performed as depicted in the example. So on the decryption side, you perform the inverse shift row transformation called inverse shift rows, and it performs the circular shift in the opposite direction for each of the last three rows. As you can see, the first row is unchanged with the 1 byte circular right shift for the second row, and the 2 byte circular right shift for the third row, and the 3 byte circular right shift for the fourth row. The second part of the diagram shows mix column transformation, and it is also done in the two directions, in the forward direction for the encryption and in the reverse direction or inverse direction for the decryption. So the forward mix column transformation is called MixColumns, and it operates on each column individually. So each byte of the column is mapped into a new value that is a function of all 4 bytes in that column. The transformation can be defined using a matrix of multiplication on the state. If you have the initial state, you define a matrix and you perform a multiplication on both of the matrix to get the resultant state. So each element in the product matrix is the sum of products of elements of one row and one column. So rationale why shift row is used is it states that it is more substantial that it may first appear. So the state as well as the cipher input and output is treated again as array of 4 byte columns. So on encryption, the first 4 bytes of the plain text are copied to the first column of the state, and so on. The round key is applied to the state column by column. Thus, a row shift moves an individual byte from one column to another, which is a linear distance of multiple of 4 bytes. For example, in the second row, it will be 1 shift, and in the third row, it will be 2 shift, and in the third row, it will be 3. In the fourth row, it will be 3 shifts. So transformation ensures that the 4 bytes of one column are spread out for the 4 different columns. So except for the first row, you can see that in each row the values are shifted. So if we have values 1, 2, 3, 4 in the one shift, it can be 2, 3, 4, 1. Again, if we have the values same here in the 1, 2, 3, 4, the values will be with the 2 shift. That means we will perform 3, 4, 2 and 1, and similarly in the 3 shifts we can move the values of 3 location. For example, we move this to here, move this to here, and so on. So every column will have different values than the initial state. Similarly, mixed column rationale gives us the coefficient of matrix based on linear code with maximal different distance between the code words ensures a good mixing among the bytes of each column. The mixed column transformation is combined with the shift row transformation, ensures that after few rounds all output bits depend on all input bits. So the multiplication by these coefficients involves at most a shift and an XOR. The coefficient of inverse makes columns are more formidable to implement. So the fourth transformation is add round key transformation, and it is also done in the forward and inverse direction. So in the 128 bit of the states are bitwise XOR with 128 bits of the round key. So the operation is viewed as column-wise operation within the 4 bytes of a state column and 1 word of the round key. So it means that one column of your input state matrix is XOR with one word of your expanded key set. So operation is viewed as column-wide operation of 4 bytes of your state column and one word of the round key. So it can also be viewed as byte level operation. So rationale for the add key transformation says that it is as simple as possible and it affects every bit of the state. So the complexity of round key expansion is plus the complexity of other stages of AES ensures the security of your AES transformation. This figure is another view of single round of Advanced Encryption Standard, emphasizing the mechanism and inputs of each transformation. So as you can see in one round we have the initial state matrix at beginning of each round. The first step is substitution of bytes, which is done by the S-box transformation or substitution, and we have seen how to create a substitution box. Then we get again the state matrix after the sub bytes, and on that sub byte we perform the substitution of rows, and in the first row we do not shift any of the values. In the second row we perform 1 bit circular left shift, and in the third row we perform 2-bit circular left shift, and in the fourth row we perform 3-bit circular left shift. And after performing the operation we again get a state matrix, and then we make a mix column matrix and multiply with our state matrix to get the mix column transformation, and it will output another state matrix which is embedded with round key matrix word, and it performs constant it is performed on a constant input and variable input from the round key matrix, and after this step a state matrix at the end of each round is produced. This concludes today's lecture, and in this lecture we discussed some of aspects of finite field arithmetic, and we overviewed the advanced encryption structure in general and detailed view that each advanced encryption standard is performed on number of rounds and varying key sizes. However, the size of input plaintext is 128 bits, and in AES structure the input is transformed into 4 by 4 matrix, and each of the value is 1 byte, and then each of the 4 by 4 matrix is stated as state matrix, and it is fed to each round of AES transformation. Usually there are 10 rounds of transformation in 16 bytes, and there are 12 rounds of transformation in 24 bytes, and there are 14 rounds of transformation in 32 bytes AES encryption. And At each transformation round, there are four transformation functions. First is known as substitute bytes, and it is done by generating a substitute box matrix, and transformation of state matrix is done by replacing the values from the substitute box. Then we perform the shift rows on the resultant matrix of substitute box, and then mixed column transformation is performed, and then finally an add round key is performed by picking up an expansion key matrix word with the input state matrix, and finally getting the output of one round, which is fed to the another round. So if you want to study more about the topic, you can read the chapter number 6 of the recommended book, or you can for further inquiries. Thank you very much.